Welcome back, everyone. In this lecture series, we're going to begin by showing you how to build out a basic Pytorch neural network. So we're going to go through the general process of creating an artificial neural network in order to create a predictive algorithm. And if you've ever done any other machine learning class or read any machine learning blogs or books online, you're probably already familiar with the iris dataset. And that's what we're going to be using for this very simple example. Later on, we'll expand to a much more complex and realistic dataset. But the iris dataset is a great dataset to just learn the mechanics of how to build out a full network. So the iris dataset, in case you're not familiar with it, contains continuous numerical data for 3 classes of flowers. So there's essentially 3 species, or 3 classes. That's Iris versicolor, Iris setosa, and Iris virginica. And this dataset contains different widths and length measurements for both the sepals and the petals. And the idea here is with those 4 features, that is sepal length and sepal width, petal length and petal width, you should be able to then predict the flower species. So we have a bunch of training data, and then we're going to train on that data and then give the measurements of a new flower and see what our model predicts. So hopefully then the network will be able to predict the class of a new flower. I want to quickly note we're going to be using object-oriented programming, or OOP, of Python. So you may want to quickly review the class keyword of Python and just some general object-oriented programming of Python before continuing in case you feel a little rusty on that subject. But let's go ahead and get started. It won't be too complex with OOP, and we'll go ahead and remind you how class structure works with Python as we build out our network. Let's get started and head over to the Jupyter Notebook. Okay, here we are at the Jupyter Notebook. I'm going to begin with just some standard imports, and in the lecture notebook that we provide for this, you can go ahead and follow along with that or follow along with this video. I'll be importing stuff as we use it, so I won't import everything at once, unlike the lecture notebook, which imports everything at the top. So I'm going to start off with just importing Torch, and then we'll be using the neural network, or NN module from Pytorch. So we'll say import torch.nn as NN, and then the last thing I want to do is say import torch.nn.functional as capital F. And this is just some convention that the Pytorch documentation uses. Go ahead and run that and import it. If you're running it for the first time, it takes a little bit of time to import. So next what we're going to do, and we'll be doing this for pretty much all the networks we create during this course, is create a model class. So I will say class, and then by convention we use a capital M on model, and then we're going to inherit from the module from neural network. So we'll say nn.module. Note here this is module, not model. So we'll call our class model and inherit from module. Then I will say colon here, and then we're going to define essentially 2 methods inside of this class. The first one is our instantiation method, which is underscore underscore init underscore underscore. Note there's 2 underscores here. Really common beginner mistake to just put 1 underscore. And then I'll go ahead and pass in self. I'll leave this blank for now. And then we'll say def forward self, and then I'll leave the rest of that blank for now. And essentially what we end up doing here is in the instantiation method, we'll do a couple things. And I'm going to kind of lay these out. First, we decide how many layers are there. And then for each layer, we basically create an attribute. And we decide on the kind of layer while we're creating this. So what we're going to do is we'll have the following. We're going to have an input layer feeding into a hidden layer, feeding into another hidden layer, which feeds to the output. And the input layer, if we know the iris dataset, that's going to essentially be those 4 features. So you have those 4 features, and then the first hidden layer, that's going to be some number of neurons n, and this is a value you can definitely play around with. And then the hidden layer 2, that's also going to be some number of neurons n. And then the output, remember we have 3 classes, those 3 species of flowers. So this is going to be 3 classes as our output. So how do we actually then define this? Well, first we're going to have attributes for each of these numbers. These 4, this neuron, this number of neurons, and then these 3 classes. And by convention, we end up saying in number of features, we'll set that equal to 4 as the default. We'll say h1 for our first hidden layer. I'll go ahead and put 8 neurons in this. and then H2 will put 9 neurons. These are really just kind of arbitrary number choices. For the sake of this lecture, I wanted to make the actual hidden layers of enough neurons so you can kind of see what's going on. Granted, this is probably overkill given how simple this data set is. There's only 4 input features, and as we mentioned previously, there's kind of no right or wrong approach to actually deciding on how many neurons the hidden layers should have. There's no set number that is correct here. However, for an intuition, you should probably have at least as many neurons as there are features. And it's up to you to add in more hidden layers or play around with these neuron sizes. Again, my choices of 8 and 9 are pretty arbitrary here. And then finally, we'll go ahead and say out features is equal to 3. So basically, the two numbers that are not arbitrary are this 4 here, because that matches up with the number of features in our data set, and this 3 here, which matches up with the number of classes. So let's actually now then construct these layers. So what I'm going to do first is I want to instantiate the module that I inherited from. So this nn.module, what I want to do is call this inherited module, I want to call its own init method. And the way we do that is we can simply say super dot underscore underscore init underscore underscore open and close parentheses. That essentially instantiates the class we're inheriting from. Then once we do that, we'll go ahead and create our layers. I'll say self dot fc1 for fully connected, and I will say nn dot linear. This is a fully connected layer, and I'm going to fully connect the input features to H1. Then we'll have another full connection, so we'll say fc2, and we'll say nn dot linear. Then we'll go H1 to H2. Note here how kind of the output of this full connection leads to the input of this one. So you might expect the next one should start with H2, which it will. We'll say self dot, and this will be the final layer, so the final connection will just call out, is equal to nn dot linear H2 and then out features. So notice already, let me go ahead and delete this pass and that comment. I was going to say, notice already that you have the ability to edit this. You can add in more layers if you wanted to, or you can play around with the number of neurons coming into these layers. The next thing we want to do is set our propagation method that propagates forward. And for this, we'll not just say self, but we'll also say x. And what we're going to do here is we'll say x is equal to f dot, so f, remember that's the functional import I did here. And this is essentially where we define the activation functions being used. And so we're going to use RELU, which stands for Rectified Linear Unit, which we already discussed in the theory lectures. And what we'll be doing here is into the rectified linear unit, we're going to pass in that first fully connected layer. We'll say fc1 of x. And then after that, we'll say x is equal to passing in self.fc2 of x. And then finally, we'll say x is equal to self.out of x. And then we return x. So essentially what we're doing here is we're taking those initial features of x and then passing them through that fully connected layer and passing that through an activation function. Then we're taking that result and putting it into the next layer and then passing that through an activation function. You can kind of think of this as in the theory when we were passing in z through the activation function and then got an output. However, here, for the sake of programming, we just keep that same variable x as we go along. If we wanted to, we could kind of make this x something like an A1 and then define A1 here, but it's easier just to kind of keep labeling everything x. So that's what we'll go ahead and do. But hopefully you can see here just a forward propagation. You've taken the features into the fully connected layer, pass that through an activation function, take that result into the next layer, pass that through its activation function, take that result, and you keep repeating this process for as many layers as you have here until you finally get the output and you return x. So that is our model, and in case you ever get any errors when running this, you can always copy and paste from our notebook that we provide for you. Next, we're going to instantiate the model using the parameter defaults, but the last thing I'm going to do is say torch.manual_seed and say, I'll just arbitrarily choose the number 32. Recall that weights and biases in a network, those are initialized randomly. So to make sure you get the exact same random initializations that I get, go ahead and set your seed to 32. Again, 32, totally arbitrary number choice. It's just making sure that you start with the same random numbers that I do. That way you get the same results that I do. And in the exact same cell, go ahead and create your model. So we'll create an instance of our model, go ahead and run this. And again, if you're getting any sort of error here, please make sure to refer to our notebook. You can always copy and paste from there. But this essentially concludes part one. So let's do a quick review of what we did. We did some fundamental imports. We created a model class object inheriting from nn.module. You'll see us do that throughout the course. Then we created an instantiation method here where we define the number of features coming in, the number of neurons in the hidden layers, the number of out features. We define the hidden layers. Since we're doing fully connected layers, that's why we choose nn.linear. We go ahead and create those as attributes. And the reason we create them as attributes is so that we can reference them in our forward propagation function, or forward propagation method, I should say, where we then pass in those initial features through the fully connected layer into the activation function, and we essentially rinse and repeat this as we go forward, just as we discussed in the theory lectures. And then we create an instance of our model, and to make sure you get the exact same random initializations, we went ahead and set that manual seed. Okay, so coming up next, we're going to load in the iris dataset, we'll plot out that dataset, and then we'll perform a train test split. I'll see you at the next lecture.